In the previous videos, we have spent some time to talk about classification problems, and we were using this kind of Bayesian framework with Gaussian as the underlying distribution. So it's a parametric um, approach, right? And we tried both the discriminative approach and also generative approaches for classification problems, right? And and we did some examples, right? We started with a very simple one-dimensional example, with with only two classes, and then we extended to two-dimensional problems, also with just two classes, and then we extended to a problem with 256 dimensions and 10 classes, right? And um, but that's for classification. But now let's talk a little bit about regression, right? We are still going to stick with this kind of Bayesian framework, and then we're still going to stick with uh, the Gaussian as the underlying distribution. So how can we understand regression problems in this kind of Gaussian Bayesian framework, right? Um, so suppose we are doing this kind of a suppose we're actually trying to actually make a prediction of some kind of function f by using a set of parameters theta j and a set of functions that we call basis functions. So phi j is a collection of our basis functions, and then theta j is just the weights in front of those basis functions, and we are doing this kind of a weighted summation of those basis functions, and we are assuming that we have this many b basis functions. So we're going to have a b theta j, right? So you can think of a theta j as just a vector with b elements, and theta j is going to be our parameters, right? So different model or different y corresponds to different values for this theta j vector, right? And if we want to use linear algebra, we can do this kind of a notation. So theta is a vector, right? We transpose it. A column vector becomes a row vector, and phi x is going to be another vector, right? Phi x is going to be another vector, and this transpose just means inner product, right? Transpose and then matrix multiplication is just going to give you this inner product. It's a kind of equivalent representation, except that we're writing it as some kind of a linear algebra operation, right? So what are some of the popular choices for those basis functions, right? In principle, this basis function can be anything. It doesn't have to be those examples I'm giving here, but in practice, these kind of basis functions are used quite often, right? So here I'm actually giving you some examples. So for example, phi x could be a vector of these kind of polynomials, right? So here we're treating x as a scalar, right? It's a kind of a one-dimensional problem, but you can extend it to multiple dimensions without too much of trouble, right? So suppose the x is a scalar, then the basis functions could be x to the 0th power, that gives you 1, right? And then x to the first power, x to the second power, up to x to the b subtract 1th power, depending upon how many basis functions you are going to use, right? That's one kind of a choice, one kind of a basis functions, right? And if you actually limit b to 2, for example, right? If you just set b to 2, then this kind of a basis functions is just going to give you two functions, right? The first one is the constant scalar 1, and the second one is x, right? So in this case, you're going to get something that's called a linear regression, right? You're trying to figure out. So in this case, theta also has just two elements, right? Theta 1 and theta 2, right? Theta 1 is going to be the interception, right? So interception. So theta 1 is going to be multiplied with 1, and theta 2 is going to be multiplied with x. That's going to be your slope. So you are trying to actually fit a straight line through a cloud of points by adjusting the interception and the slope of the line, right? That's linear regression, but you can also include those higher order polynomials of x, right? So if you extend it to multiple dimensions, then suppose you have a two-dimensional problem, x and y, right? So then your basis function is not going to be just polynomials of x anymore. It's going to be polynomials of both x and y, and also x multiplied y, right? So your first is going to be 1, right? The second is going to be x, and then third is going to be y, right? And then the fourth is going to be x squared, right? And then following that is going to be x multiplied y, and then following that is going to be y squared, and then goes on like that, right? That's going to be your basic function for a two-dimensional problem. In principle, you are trying to fit two-dimensional surfaces onto a cloud of points, right? So that's one possible choice of basis functions, right? But that's not the only choice. Some other popular choices include those kind of trigonometry functions. Again, we're treating x as a kind of a one-dimensional problem, right? So x is just a scalar. So for zero frequency, the DC component 1, right? And then sine x, cosine 2x, cosine 2x. Of course, the factors here doesn't have to be integers, right? You can sort of include multiple different choices, different frequencies corresponding to different wave numbers or frequencies, and then up to m, right? Up to m. So that's another possibility for choosing basis functions, right? And those basis functions can be so these choices for the basis functions do not actually depend upon the training data, right? So those basis functions are kind of independent of the training data, right? So if you are given a set of training data, x squared, this kind of thing, sine x, cosine x, you don't see any training data in it, right? So it's general. This is general, right? But another popular choice is to use something that's called kernel functions, and those kernel functions actually depends upon your training data set, right? So each of the kernel function has two variables, x and xj, right? And one popular choice is this kind of a Gaussian functions. These kind of Gaussian functions as kernel functions, what they call kernel functions, right? So xj is sort of the center of those Gaussian functions, right? And those xj, those center can be selected, can locate at the location of those training data, right? And depending upon how many training data you're going to have, the total number of basis functions in this kernel function set is going to be identical to the number of training data that's given to you, right? So if you have many training data, then this basis function is going to this set of basis functions are going to have lots of functions inside of it, right? And then this summation is going to take more functions, more basis functions, right? We're going to look at in our examples, we're going to look at this kind of basis function and also this kind of basis function, right? We're going to skip. If we have time, we'll look at this polynomial basis, right? Because this polynomial basis has been discussed quite frequently in other people's videos or in textbooks, right? But here, let's spend some time to talk about this kind of basis function and this kind of basis function. That might give you some interesting discoveries, right? Give you some new insights, right? So in principle, our different model just corresponds to the different choices or different values of this theta vector, right? But how do we actually use this? How do we actually utilize this Bayesian and Gaussian Bayesian framework, right? So if we want to use the Bayesian framework, we need to define what's going to be the conditional probability and what's going to be the prior. Later on, once we sort of start to look into the prior, you're going to see prior actually corresponds to different kinds of regularization terms, right? So we're going to do this kind of thing. We're going to, so for every training data set xi, it's going to have a, because it's training data, so it's going to have a label fi, right? In our classification problems, this fi is discrete, so it just corresponds to a discrete set of classes, right? Different categories, right? But here, fi could be a real number. It's continuous, right? It doesn't have to be discrete, right? But this label is actually given to you because you are dealing with training data, right? And then on the other hand, we have this particular formula to actually make a prediction about the label using those feature sets xi. Right, xi is going to be our training data, the feature of our training data, right? And then we're going to do a subtraction. And then, unless your prediction is perfect, otherwise this subtraction is not going to be 0. Right? And then we are going to denote the residual as epsilon I. So for the ith training data set, we're going to have a residual called epsilon I, which is just the difference between the actual given label fi and the prediction based upon our sort of linear in parameter model f using the feature sets of the ith training data, right? And that's going to be our residual. And we're going to assume that this residual, this epsilon I, is going to follow a normal distribution with 0 mean, right? So the mean is going to be 0, right? So epsilon I is going to be a distribution, right? It's going to be a normal distribution, and the average or the mean for that normal distribution is going to be 0, right? And then the conditional probability for epsilon I given theta, given a particular choice of theta, given a particular choice of model, is just going to be this Gaussian, right? And then with this particular factor in front, and then exponential function minus epsilon I squared divided by sigma I. Sigma I is the variance for the ith data, for the ith training data, right? And if we want to bring the expression for epsilon I into this Gaussian, then we have this expanded expression for this conditional probability, right? So what does this conditional probability actually telling us, right? So suppose the horizontal axis is the feature x, vertical axis is f, vertical axis is f, right? And then the data, the green dots here corresponds to fi. That's the actual observed label, right? And then this red curve that's given here is actually the prediction f, the prediction based upon all the different values of x, right? So for every training data, say x1, x2, and x3, we have 3 training data here. What we are actually essentially constructing is some kind of Gaussian, right? Some kind of Gaussian, and this Gaussian is going to be centered around f, the prediction, right? The peak of the Gaussian is going to be located at the location of the prediction f, right? And then it's going to have a width that's given by sigma I, or the square root of sigma I. That's going to be the width of the Gaussian, right? So what this conditional probability is telling us is that the probability for epsilon I, is going to, for a given model, for a given theta, the probability of epsilon I is going to follow this kind of a Gaussian with a center that's given by f, by the prediction, right? And then the width is going to given by sigma I, right? So what kind of epsilon I is going to give you higher probability, right? What kind of epsilon I is going to give you higher probability? If the epsilon I is close to 0, then your probability is going to be bigger, right? Epsilon I close to 0 means what? Means your prediction is very close to the actual observed label, right? Then that's going to give you a very large probability, right? And then what kind of epsilon I is going to give you a small probability, right? If epsilon I is big, then the probability is going to be small, right? How do you actually get big epsilon I? Which means your prediction f is very different from the actual observed label fi, right? So for good predictions, your conditional probability is going to be big. For poor predictions, then your conditional probability is going to be small, right? But how good the prediction is going to be depends upon what? Depends upon your model theta, right? If you happen to have selected a very good theta, then this difference could be very small, right? Your label and your prediction are going to be very similar. In that case, the conditional probability is going to be big, right? But if you happen to choose a very poor theta, the theta is not so good, then this prediction could be very different from the actual observed label of Fi, right? Epsilon I is going to be big, and then this conditional probability is going to be small, right? So that's going to be how we actually utilize this kind of Gaussian distribution to implement this kind of a, or to describe this kind of regression problem, right? So now the problem is how do we actually maximize this probability, right? Maximize this probability. So again, we are going to follow the same kind of a procedure as in the classification problem. So we define the likelihood function, which is a function of theta, right? Because epsilon I is a given for a given theta. Epsilon I is a given for a given theta, right? So it's going to be a function of theta. We're doing this kind of training process, right? So the observed label and the training data are actually given to us. And then because they are independent, so we can do this kind of multiplication for different training data, right? And we have n training data. And then we can take the natural log of this likelihood, right? And this multiplication becomes a summation. The natural log goes into the individual conditional probability, right? And now if we actually do some simplifications, we're going to get this summation, subtract 1/2 this particular summation, right? And at this point, one of the popular choices for sigma I is to assume that sigma 1 equals to sigma 2 equals to a common sigma. So here all the different Gaussians, we're assuming all the different Gaussians are going to have exactly the same width, right? And if we do that, maximizing this log likelihood, is kind of equivalent to minimizing this part, because sigma I is a common constant, so we can take it out, and then it's equivalent to minimizing this particular function, right? Because we have to actually account for this minus sign, right? So maximizing this negative function with the minus sign is equivalent to minimizing this j function without the minus sign here, right? And considering this prediction, f can be expressed as this linear algebra operation here, theta transpose phi, which is this particular weighted summation of the basis functions, right? And the basis functions are evaluated at the training data, xi, right? At the xi, so you take xi into it, right? And this j theta is just going to be a theta. It is just going to be a function of theta. Now you take the derivative of j theta with respect to theta, and that's going to give you this this linear algebra equation that looks quite complicated, but it's actually quite simple if you actually pay attention to what's actually being written here. So phi is a vector of the basis functions that's evaluated at all the different training data, right? And then f, this boldface f, is going to be a vector with elements given by fi for all the different training data. And then subtract phi transpose is, so phi transpose is a vector transposed, so it's a row vector. This is a column vector. That's going to give you a scalar, right? That's going to give you a scalar. And then phi transpose is another vector, right? Row vector, column vector. So row vector times a column vector, that's a scalar, right? Theta, subtract the theta. Oh no, sorry. I think I got the. No, phi is not really a vector, right? Phi is actually a matrix. So here I'm actually giving you the exact form of the phi matrix, right? So the reason that the phi here is a vector is because there is a summation over here, right? There is a summation over here, but here we're actually getting rid of this particular summation, so we have to actually expand phi into a matrix, right? And this matrix is actually given here. So a little bit of a notation difference. So this phi is going to be a vector, but the phi here is going to be this particular matrix, right? And F is still going to be a vector with all the elements given by Fi. Right? And this matrix is gonna have this kind of dimensions. So the total number of rows is gonna be the same as the total number of training data. So x1 to xn. And then the number of columns are going to be equal to the number of basis functions. So phi 1 goes to phi b, right? And then f is going to have how many elements? It's going to have n elements, right? So phi transpose is going to be a matrix that's b by n, right? B by n times another vector. That's n by 1, right? The multiplication is gonna give you a b by 1 vector, and then you subtract phi transpose times phi. That's gonna be b by b, right? B by b matrix. This b by b matrix is gonna multiply with the vector theta. This vector theta is gonna be b by 1. Right, so multiply them together, it's going to give you a vector that's b by 1. So a b by 1 vector subtract a b by 1 vector has to equal to a 0 vector, which is also b by 1, right? And then if you actually try to solve this particular equation using linear algebra, the optimal theta value based upon this maximum likelihood estimate is going to be just this particular expression based upon linear algebra. So all you have to do is to actually move this term to the right hand side of the equation, and then get the inverse of phi transpose times phi, right? And then you get the maximum likelihood estimate of the optimal theta, right? And this matrix phi is called the design matrix. It's called design matrix, and this design matrix only depends upon the training data and the form of the basis function. It doesn't actually depend upon anything else. So as long as you're given a set of training data and you have selected the form of those basis functions, this design matrix should be able to actually is available to you. All you have to do is to actually compute each of the individual elements, and then you get the matrix, and then stick those matrices into this linear algebra expression. It's going to give you the optimal estimate of the theta, right? And this particular form is called least square regression, and this least square regression is actually used very widely. In practice, and it's a very useful form, right? At this point, there are a few things we can do to make it even more general, right? Don't forget that we have made this assumption that sigma 1 equals to sigma 2 equals to a common sigma, right? But in practice, we don't really have to. We don't have to assume the sigma is the same for different training data, right? So for some training data, you may have a higher confidence than other training data. In that case, you could actually make sigma smaller, make the Gaussian narrower, because you are quite certain that this particular training data is quite accurate, right? In that case, sigma I can be set to be a smaller value, right? So depending upon the weights you are gonna put onto different training data, you can make sigma I different for different training data, right? And in practice, that's a quite useful extension. It's a quite useful extension. So how do you actually do that, right? How do you actually do that? So now J theta is no longer just this particular function anymore. J theta includes sigma I. Right, that's the second part of this logged likelihood, right? And then here we introduce Wi, that's the weight for the ith training data, equals to 1 over sigma I, right? And then J theta becomes this Wi times Fi subtract f xi theta squared, right? And now we can take the derivative of j with respect to theta and then set the derivative to 0, right? And then we're going to end up with a linear algebra equation that looks very similar to the equation here, right? And then we're going to have to solve that linear algebra equation, and then the maximum likelihood estimate theta hat is just going to be like this kind of thing, right? So modification is not so big. It's very similar to here, right? The only thing that's different is that you have to stick a w in the middle of phi transpose and phi, and then stick a w behind phi transpose and between phi transpose and f here, right? And this w matrix is just the diagonal. It's just a diagonal matrix with w1, wn, w1, w2 up to wn on the diagonal. And wi is given by 1 over sigma I, right? So you can design this weight matrix to account for the possibility that some of the training data might be more accurate than other training data, right? In that case, you make sigma I smaller for that particular accurate training data, and then making sigma I smaller, it just means wi is larger, right? Wi is going to be larger. In that case, you can give the accurate data with a higher weight. So that's how you can account for different weights for different training data. And there's another also useful extension, which is by considering the posterior, right? So the posterior for theta is proportional to the conditional given a specific theta times the prior h theta, right? So the conditional of p epsilon, so this boldface epsilon is going to be a vector with epsilon I as its elements, right? And then p epsilon given theta is just the L theta, right? The likelihood function. And this likelihood function is just a multiplication of individual conditional probability p epsilon I theta times the prior h theta, right? So far we have been assuming that the prior is always uniform, right? We have been assuming that the prior is uniform, so that's why maximum likelihood estimate is going to be identical to the maximum a posterior estimates, right? So we have been making that assumption so far, right? But this assumption can be relaxed. You don't have to assume that the prior is uniform, right? So here the likelihood, the conditional probability is given by this particular Gaussian, right? And we can actually introduce a prior for h theta that's also a Gaussian, right? So what does it mean, right? What does this Gaussian actually mean, right? So this Gaussian is just purely a function of theta, right? There's there's no training data or observation that's involved in constructing this prior, right? And what's gonna be those Gaussian functions, right? First of all, you can sort of see the sigma I. So the number of Gaussians inside of this multiplication is equal to the number of elements in the theta vector, right? That's the weights. That's the weights here, right? So how many basis functions you're going to have? You're going to have b basis functions. You're going to have b elements for the theta vector, right? So for theta j, right? So how many Gaussians you have, right? That's b Gaussians, and each Gaussian corresponds to a particular function of a Gaussian function of theta j with 0 as its mean. So you're assigning those theta j that's closer to 0 with a higher probability, right? Of course, you don't have to actually use 0 as your mean, right? Suppose you have some idea about what's supposed to be the correct value for some of the theta. Then you can just set the mean for that particular theta j to the assumed value, right? So it doesn't have to be theta j squared. It can be theta j subtract some previously assumed bias, and then the subtraction squared, right? And then you have to give it some uncertainty, right? Here we are using tau j for theta j, right? That's the width of the Gaussian, right? But as it's written here, you are actually preferring a theta j that's close to 0, right? You prefer theta j that's close to 0. You want your weights to be as close to 0 as possible. That's your assumption. That's your prior. You prefer those theta j values, right? So now because this h theta is no longer a uniform distribution, it's a Gaussian distribution now. So we can the maximum likelihood estimate is different. It's going to be different from the MAP, or maximum a posteriori estimate, right? And in this case, if we want to use the MAP, the maximum a posterior rule, then we have to actually maximize the log of the posterior, right? And maximizing this posterior is actually equivalent to minimizing this particular function of theta. Here we have accounted for the different weights, Wi, for the different training data, right? So the first term here is identical to this part of the expression, right? Which measures how good the data is being fit, right? And then we have to add a second term here, right? The second term, lambda over 2, and then summation j over j from 1 to b theta j square, is a measure of how different theta j is from 0. So how big theta j actually is. You would prefer small theta j, but or prefer small theta j square, but in practice it may not be 0, right? So you add a term to quantify how big theta j actually is. And then what's going to be the lambda, right? What's going to be the lambda is just going to be the width of the Gaussian that you have specified in your prior, right? It's just 1 over the width of the Gaussian. And here you have assumed that tau j equals to tau 1 equals to tau 2 equals to tau b, right? So if you assume all the different taus are identical to the same value, then lambda can be taken out of the multiplication or summation, and then you get lambda over 2, right? Of course, this is one of those assumptions that you make, right? It doesn't have to be. So if tau 1 is different from tau 2 different from tau b, then you cannot actually take the common factor out. You have to actually multiply something in front, just like how you actually deal with the weights for the different data, right? The different sigma for different data or different training data, right? But here, let's just assume tau j is the same for different theta j, right? And in this case, you can take a derivative of j theta and then set the derivative to 0. And if you try to actually solve that particular equation, you're going to get a theta hat that's the MAP estimate. It's not MLE estimate. It's a maximum a posterior estimate, which is going to look like this kind of thing, right? It's still going to be very similar to this expression, right? Except that inside of this parenthesis, you have to actually subtract something, or plus something, plus lambda I, and then take the inverse. Right. I is the identity matrix, so it's going to be a diagonal matrix with 1 on the diagonal, right? Lambda is going to be a scalar. Right? You have to construct this matrix and then take its inverse, and then multiply with the remaining part of the expression, right? And this particular way for regression is called rich regression. It's called rich regression in the regression literature, right? It gives you some way to balance the need to fit the data, and also you don't want to overfit the data by introducing very large theta j, right? You want to make the theta j very small, and at the same time you want to fit the data, right? You want to sort of make a compromise between these two goals of fitting data and making the weights very making theta j, your parameters very small, right? And this is called ridge regression.